Okay, so it's a great pleasure to be here. Thank you very much. And it's a great pleasure to be also in this building here. I think it's very important historically. So, but I would like today to give a talk that will be more applied than the one we've seen before. It's more like avenue that we have been looking for to enhance the skills of dynamical prediction. And what I mean by dynamical prediction, I'm really referring to what we call seasonal to decadal climate prediction. So seasonal to decadal prediction, it's prediction where both depending on the initial condition, meaning that the accuracy of the initial condition are going to influence variability on this time scale, but also it starts to be influenced significantly by the response or sensitivity to the forcing. And so it's a bit of a simplistic view of what is where the predictability resides, but because it's a coupled system, so you have more timescales influence. But what we know is that when we go beyond 30 days, the timescale that have the largest predictability is most likely the ocean. So yeah, so what I will try to show is to show a little bit how we are now going into providing this kind of prediction, and how I see how we have been trying to improve this kind of prediction system. So we use the Norwegian Earth system model as a dynamical system. It's one of the systems that has been widely used for CEB 5, way before actually, but also for CEB 6. It's based on CSM. The main difference is that the ocean model is isopycnal ocean coordinate model, and you also have different biochemistry and chemistry in the atmosphere. And we use the ensemble Kalman filter data simulation, so we assimilate data in that. And we really try to have long-term reconstruction for the whole century, and also try to provide some kind of prediction. I know that there is actually emerging interest of this kind of prediction from the hydropower, from the fisheries, and from insurance company. So it's a growing field. It's very new, but it's growing rapidly. So one of the aspects of the system that is quite particular is that we use dynamical covariance. So I think everyone here knows that dynamical covariance is good because, in particular, for climate prediction, that is a stochastic problem. It's important to have an ensemble to account for the uncertainty of the prediction, but also, of course, because the climate have some regime shifts, and this is one of notorious shifts that you have in subpolar gyre. So that's a place where one of the hot places where you have convection. So meaning that where you generate this kind of deep water, and you see that when the gyre is in a very strong mode, so before the 95, that you have very deep mixed layer, the very intense subpolar gyre, and then you have a very strong signature of the deep convection below, while after the 95 shift, the mixed layer is very shallow, and the signature of the deep convection is not as large. So yeah, flow-dependent covariance is very important for the climate system. Yeah. Another very strong asset of the system is that we are using isopycnal coordinate. And what we find is it's very important to organize the covariance or use the data simulation system in a way that is coherent with the dynamical behavior of the system. So in the ocean, very often you get like a front, and you will get the position of the front that will also be seen very deep in the isopycnal signature. So what we did is that we organize again in this place where you have the deep convection, we show the correlation between the sea surface temperature in the interior. And we show it when organized in isopycnal coordinate, and when we interpolate all the members from the isopycnal coordinate in very, very, very high resolution, and we calculate the correlation again. And when we look into isopycnal coordinate, we see the signature of the deep convection again, while when we organize it in Z coordinates, it is basically gone because the position is in all of the place, and this basically blur out all the things. So our point is that if you organize better the covariance, you may not need so much localization, or you may not need to cut the covariance in the interior. And so we've been testing the system very simple, just using SST assimilation. So we assimilate SST in the ocean model, and we try to run a seasonal prediction. And just using SST, we were able to achieve actually better skill than the average skill of the North American multimodal ensemble seasonal prediction for SST, but also for other quantity. And actually, we have been ranging them in different bins of what we call better system, the worst system, or similar, meaning that none system is better than another. And we, most of the time, end up in similar or better bin. So when we thought about improving the system, one of the other avenues was initializing sea ice. So sea ice is another place, in particular in the Arctic, where there is a big source of predictability. And the major source of observation that you have in the Arctic is this, what you call ice concentration, so the fraction of ice you have within a grid cell. And this fraction of ice is from satellite, so you only know the area. You don't know if it's thick ice, you don't know if it's thin ice. But the model does represent this kind of multi-category of ice. And that was a very nice study in twin experiment that when we actually use this aggregated sea ice, but we update with flow-dependent covariance the multi-category of sea ice, we were able to really reduce drastically the error in ice thickness. And I think the pointer is dead now. So you had a large improvement in the ice thickness when we account for the multi-category of ice. And also, as expected, I mean, you have other studies that show that before that strongly couple data assimilation, in a sense that when you update the sea ice, you should also update the ocean to make better use of the data and also have a more dynamical, consistent state is important. So we have been applying that in the real framework, and indeed, when we run a seasonal prediction of sea ice extents in many different regions, we can see that the prediction skill is greatly improved by complementing the system with sea ice assimilation.
What do you mean by category?
So the sea ice, you have different categories. So you have like what they call thin ice, so it's very young ice that is very fragile, and you have different thermodynamic properties. While the thick ice is more, so you have different class of category.
The amount of ice per category can change? Or
yeah, of course. So every grid cell, but what you observe is the area. So it can be like thick ice, or it can be a lot of sea ice, or it can be thin ice. But in the ensemble, so you have a model with different category of ice. So yeah, so yeah. But so you see here that the prediction varies seasonally, but typically, yeah, adding sea ice has been greatly improving our prediction skill. The surprising thing for us was that we thought about it. I mean, it seems that this strongly coupled DA is important, meaning that we can use sea ice observation to constrain the ocean. But we try then to do the opposite. What happens when you use ocean data and you try to constrain the sea ice? So no, we have been trying exactly the same thing. We say we have ocean data for a very long period of time, from the beginning of the century, and we try to say, can we constrain sea ice variability? And we constrain the multi-category sea ice variability using the same formulation of covariance that I was proposing before. And we see that this is a RMST that you have in the free run on the left when we do weakly coupled DA, meaning that we only update the ocean quantity. And when we update also the sea ice from ocean data, we can see that basically a lot of the error in the sea ice is gone, in the ice thickness. And ice thickness is really the key quantity for having good prediction in the Arctic. So it really shows that if you organize your covariance in a dynamical, consistent sense, you can really get a lot of benefit from the DA. Okay, so that was very much on the seasonal timescale. We also, as I was saying, in some region of the globe, there is skill that goes way beyond seasonal timescale. And luckily enough, being in Norway, Norway is one of the regions. We got everything. We got oil, we got hydropower, and now we got predictability on decadal timescale. Yeah, but so what you can see is that it takes about 6 years for large hydrographic anomaly. You see it a little bit here. you see SST in this grid cell, and you see that you have some kind of long-term anomaly. And this anomaly here has been shown to be really correlated with sea ice variability, because this water will be advected into the Arctic. It's been connected to temperature over Norway, precipitation over Norway, sea ice, I say, and also now recently to cod, the cod population. So no, a lot of people start to get interested, say, what will be the cod 6 years ahead? And so we are able to get some kind of good, or some significant skill up to 6 years ahead. But since this mechanism is quite well understood, that you have this propagation of anomaly from this grid cell to this grid cell, if you look at the data at the correlation with lag at the previous station, you see that in 6 years, this anomaly will be propagating and ending up in the Barents Sea. So we have a mechanism of predictability, and we can look how it is in the model. If we look in our model, it takes about 3 years to propagate this anomaly. So we know that our model, if we place a correct anomaly initially, it will be moving too quickly into this place. So we'll be out of phase at some point. So ideally, we would like to use this model, but we can't afford running our big system with such an expensive system. So we have been trying to use hybrid covariance approach. So we are always one lag. I mean, we are always late compared to the atmospheric people and all the other people. But so we have been trying that, and I would try to bring maybe something new. So hybrid covariance, you blend linearly dynamical covariance from ensemble, which have a lot of sampling error, and you try to complement it with a large, stable static covariance or climatological covariance. So it's not new, and you don't need to formulate the covariance. You can just find a formulation with ensemble anomaly. So you can hybridize with climatology. That is not new either. Or you can hybridize with two resolution systems, saying that I have a model, I will run an ensemble of the same model at a lower resolution. Actually, something I think is used also for the outer loop in 4D VAR. But now we try also, can we do a combination of the two methods? Can we, because you have a flow dependent, which is have a limitation of number of members, and you will have a static where you have no limitation of ensemble size. So we use a quasi-geostrophic model. So we have two versions of the model. We have the high resolution version, the low resolution version. And note that because the low resolution is 4 times coarser, it is 16 times faster, because you can increase the time step by a factor 2. So basically for running one high resolution, you can run 16 low resolution model. Okay? So now we compare the different methods at equivalent computational cost. Okay? And we run the result at optimal blending coefficient, so this linear alpha, and also at optimal proportion between the high resolution and low resolution. So you have an infinite number of members you can pull from both. So we have run a lot of simulation. And here is the summary. So it took a lot of time a lot of simulation to run this thing. But what you see here is that, so ENKF will start working about 20 members with this system, and performance are improving as you increase the ensemble size. So these computational resources needed for the high resolution version of the system. Okay? The hybrid static covariant that is used a lot is improving, in particularly for low ensemble size. This is not new. What we find quite new is that the dual resolution is actually outperforming by quite a big margin the skills compared to the static covariance, hybrid covariance. So it seems that the flow dependency, although the dynamic of the system is a bit not as good as a high resolution, it's still better to have flow dependent covariance with a poorer model than having static covariance. And at some point, this dual resolution stopped working because you got too few members in your low resolution to get stable performance. Just as a side note, it takes about 50 dynamical members in the low resolution version of the system to get a high resolution working. So now we get a bit of a complete picture. Depending on what is our computational resources, we can choose which method will work the best for us. And so we've been trying that now with our real system. And because we started this analysis before we got this result, we choose hybridation with a static. So not the one that is best, but I mean, yeah. So it's always the same when you do parallel thing. We will run the dual soon. So we did a 10-year analysis, monthly assimilation. We assimilate SST. And we update the full water column. And we try to see what are the reduction of error. And what you see here is the RMSE, global RMSE of temperature. So you assimilate SST, and you see that assimilation have reduced error, most likely in the surface. Okay. On the right-hand side, you see the reduction in percentage of RMSE. So positive means that you have reduced in percentage of error from the free run. So in the surface, we reduce by almost 50%, but in the deep, we reduce by about 10%. For temperature, there is not much difference. But what was quite interesting is that for salinity, we can clearly see that the EN curve was yielding a very degradation in the intermediate water. And this is barely gone now in this version. So we clearly see that this will allow us to run the system without localization and containing the drift. So we don't have basically this adjustment that goes afterwards. Yeah. So now I'm moving for the second part of the last part of the talk. How much time? 5 minutes? Yeah, so I will try to be brief. But the big elephant in a room when you do climate prediction is that the model have bias that are extremely large. And the bias is actually larger than the signal we try to analyze or predict. So, and the progress that has been in the past generation of CMIP is actually very, very, very minor. And it's quite scary. But so we are running with systems that have very large bias, and we try to yield prediction with that. And DA is not designed to have model with bias. So there's many ad hoc methods to handle this bias, but none are good, actually. So the common approach that is used in many ensembles is called super ensembles. You run all the system independently, and you do an average of them afterwards, hoping that the bias will kind of compensate each other. And so we've been trying now to move towards something called supermodeling. So I give a very brief introduction of what supermodel is about. And there will be many other talks. So I will give afterwards a talk, Francine as well, of what supermodel is. But typically, if you see this Lorentz 63, you see the tree equation. Here, we assume the truth, which is a black line here. With this parameter, we have 3 imperfect models, one in the left wing of the butterfly, one on the right wing of the butterfly, and the other one that is quite good, but still large amplification. So what you do is that you put connectors between dynamic, as you run the models forward in time, you put connectors between the different imperfect models. So you see that the tendency in the x variable for model 1 will be nudge towards model 2 and towards model 3. So you have first a training phase where you're able to play with this nudging term. So you can attract the model, you can pull the models to the new dynamical regime. And then in a verification phase, you're not able to play, you fix this nudging coefficient, and then you run the model as a new dynamical system. So in this example here, you see that this is when you take the average of the 3 model, it looks like a ball, a snowball. But after you have trained this nudging coefficient, you end up having the 3 models that have the right behavior of the attractors and the mean looking pretty much like the truth. So then afterwards, you can just use this system and run a prediction with that, and then you have a bias-free model without knowing if it's a parameter, without knowing it. So the models are completely independent. They are black box from each other. They are just communicating. So there is different flavor of supermodeling. You have what I call the connected supermodel. That was the one I was showing before. So you need 2 times the number of models to estimate. Parameter nudging is bounded. So it's not very good to estimate. It's very challenging to estimate bounded parameter. and you need to tune that to achieve synchronization and optimal solution. Another type of supermodel is what we call weighted supermodel, where you replace the states by a weighted mean of the three independent model. And the final one is model. So the problem is that when you run with real model, variables are different. Grid is different. They are running at different speed. So since they're running at different speed, you can't do that because you will be suboptimal. Since they are not the same variable, you can't replace the variable because the model will simply blow out. So what we are doing is that we are generating some kind of synthetic observation that we are assimilating back into every single individual model. And so we get synchronization without getting the model to blow out. Okay, so we are in the starting phase of this supermodel for a system model, but we have three system models: CSM, MPA-ESM, nous-ESM. And for the atmosphere, we do synchronization based on spectral nudging. And for this is ongoing work, so it's not achieved, it's not a done deal. And for the ocean, we aim at generating synthetic observation and assimilating them back. And we have started by equal weights. We have to tune the observation uncertainty, so it's more like our assimilation strengths. And we use ENOI in each of the models. And so right now we wonder, can we achieve synchronization with this simple thing? So we can see that the variability has been synchronized. So here I show an example of ENSO. So we see that ENSO variability is quite nicely synchronized between the three models, which is obviously not in the other model. The bias is also reduced. So you see the bias of SST in the three unconnected model, and the bias in the three connected model is actually improved. So not by much, but we haven't tuned the weight. No, we are just equal weight. But the big bottleneck was that our variability was overly damped. So we have not managed to get a supermodel that have the right variability comparable to the observation. And it's even lower than the mean of unconnected model. If we, 1 minute? Yeah, so I'm wrapping up. So if we are using only one model, if we are pulling all the models to one, we don't have this issue. And yeah, so I will just conclude on this slide, is that basically what seems to be the case is that you need to, right now we are doing monthly synchronization only using SST, but it seems to be important to play with the assimilation frequency, to play with the nudging frequency, and you may end up in a place where we call oscillation death zone. So you dump completely, you end up in a like flat variability if you're not satisfying all these things. So we are now playing. We have been improving the variability by increasing this assimilation strengths, and we are carrying now simulation with weekly synchronization and trying to add more data. Yeah, so I think that's bringing me to the conclusion, but since I'm a bit short, I think I will just stop here.
Very much in time, thanks. Question for François? I'm going to bring you the microphone.
This one?
Thank you, François, for this very nice talk. And it's very interesting to see what is happening with super modeling, in fact, what you have there. You are clearly modifying the dynamics of these systems. For example, in the Lorentz system, did you try to look at the dynamics of the coupled Lorentz systems in, let's say, the Lyapunov exponents and things like that?
So there is a lot of study, and I mean, you will see later, and you will see in Francine that, for example, there is also a study where they use two atmospheric from the same model. So they were it's called interactive ensemble, where they synchronize the fluxes from 2 atmospheric models into 1 ocean model. And playing with the weights, they could have the double ITCZ that will much better look like a single ITCZ in the precipitation band. So there they were using this weighted sumo that was supermodel that I was talking about. So it has been applied to a lot of increasing of complexity of models. But so right now, the technical the challenge that we are facing here, that the models they are totally different. They have different variables, different speed, different things. But if you want, I can provide you a lot of literature on that and of how they're working. And yeah, there is a paper by Gregory Duran and Noel Kineside on chaos, where they look how you move from the double ITCZ to the single ITCZ. And I'm sure Lenny Smith and I have a lot of paper on that as well, with CPT and yeah.
Thinking about Western boundary currents, most models have biases of the same sign. So
yeah.
In this multi-model
yeah, so that's maybe one advantage of the. So actually, that's maybe I don't know how much Francine will discuss, but she's always defining this kind of convex envelope. So you need to have like a convex. You need to have your models around the truth to have a good supermodel. That's only rely if you have positive weight. If you have negative weight, you can surely push the model out of the convex envelope. But it's also a case that has been put many times, and Francine always said that it's good to have a bad model sometimes for a supermodel. So it's good to bring a bad model if you want to improve your supermodel. So you should have, it's very good if you can bring a convex envelope, but maybe a negative weight can also be helpful.
Okay, let's try again.